Hello, hello. If I am not mistaken, I should be live, which means that, yeah, we made it to episode 2. Unbelievable that I stick with it. So today is a bit later than I expected. I had some random stuff coming up, so I'm not sure how long we're gonna go. But yeah, so let's take a look briefly at what we did last time, because I already forgot. So yeah, we saw the very basics of Rust. We wrote one or two Hello World programs, including this guessing game. We saw how to use cargo to install dependencies. We do not want an extension. We briefly look at a few very cool Rust features. The coolest so far for me is this match in combo with the result of parse, which is literally a result that can be either okay or error, which allows this very nice pattern to handle errors, which I think it's really great. And this other thing is this other small thing is this mute keyword that basically says that this variable can be mutated. I should have checked how mute is pronounced, but I didn't, of course. So yeah, I think everything else on the screen should be pretty self-explanatory. So I think we can go ahead with our book. So let's see. Common programming concepts. This chapter covers concepts that appear in almost every programming language and how they work in Rust. None of the concepts presented in this chapter are unique to Rust, but we'll discuss them in the context of Rust. Okay. We learn about variables, basic types, functions, comments, and control flow. All the cool stuff. This foundation will be in a Rails program, and learning them will keep blah blah blah. Okay. Okay. Oh, okay. Variables and mutability. So I guess we're gonna discuss a bit more how this mute thing works. By default, variables are immutable. This I really like. One of the main nudges Rust gives you. Nudges. What does nudges mean? Push gently. Nudges. Okay, I see. It's something not very pleasant, I guess. But honestly, I really love it. However, you still have the option to make your variables mutable. Okay, I think this is a very good default. Is basically what Kotlin did versus Java. Like for example, a stupid example, but if you create a list in Java, it's mutable by default. But like the vast majority of cases, you don't want your list or your collections to be mutable. And so instead of having list in Java and then immutable list in Guava, for example, in Kotlin you have lists, which by default is immutable, and then you have mutable list. So you need to be so the default is not to be mutable, which I think makes a lot of sense. Same for classes that in Kotlin are closed by default and in Java are open by default, etc. When a variable is immutable, once a value is bound to a name, you can't change that value. To illustrate this, let's generate a new project called variables in your project directory using cargo new variables. Okay, so we need a new. So let's go back. I have my headphones cable really not playing nice. Yeah, I need to improve my setup here. Cargo new variables. There we go, inside the project. We open it again, and we will have our nice hello world. Okay, so what do we do? I don't want Docker extension. So what do? We create a variable x, which is 5. This is not mutable because we didn't use mute. And then we print its value. value x, and then we assign a new variable to it, and I guess this will not compile. Let's see. Yeah, I should really learn a few keyboard shortcuts for Visual Studio Code. I don't normally use it at work. So let's see, cargo run. And in fact, first assignment to x, consider making this binding mutable. Okay, exactly what we expected. Cannot assign twice to mutable variable. I have to say that these are the errors that Rust C generates are beautiful. Like, these are the best compiler errors that I've ever seen. Save and run the program using cargo run. Yeah, we are seeing this error. This sample shows how the compiler helps you find the errors in your program. Okay, there are messages indicate that cause of the error is that you cannot assign twice to immutable variable x because you try to assign a second value to the immutable x variable. Okay. It's important that we get compile time errors when we attempt to change a value that's designed that is immutable, because this is very situational related to bugs. Okay. The cause of this kind of okay. The Rust compiler guarantees that when you state a value won't change, it really won't change, so you don't have to keep track of it yourself. Okay. Mutability can be useful. That's why we have mute. Blah blah blah. Okay. And then we make it compile basically. Okay, so we can just mark x as mute, and then it will work. It can change the values. Okay, cool. Constants. So like immutable variables, constants are values that are bound to a name and are not allowed to change, but there are a few differences between constants and variables. Let me take a random guess. Not very random. I would say that I guess that a constant must be such at build time. Also, Kotlin has this concept that you can have you have vals, which are basically final variables in Java, and then you can also have const, which indicates that they are constant even at compile time. Let's see what Rust means by const. You declare constant using the const keyword instead of let, and the type of the value must be annotated. Okay, so you must specify the type. Like here, we are not saying that this is like a unsigned 8-bit number or whatever. Is it even a real type? It is. Nice. Okay, so this would be inferred, but for constant, we would need to explicitly state it. Constant can be declared in any scope, including a global scope, which makes them useful for values that many parts of the code need to know about, which is usually the case for stuff like compile time constants. The last difference is that constant may be set only at a constant expression, not the result of a value that could only be computed at runtime. So yeah, in effect, they are literally are compile time constants. For example, 3 hours in seconds, blah blah. Okay, we see that we are stating the type explicitly, and this can be done by the compiler, like so that you can compile the actual result of this as an expression rather than the expression itself. Okay, constants follow the same naming convention on Java. Basically, they are uppercase with underscores. The compiler is able to evaluate a limited set of operations at compile time, which lets us choose to write out this value in a way that's easier to understand and verify rather than setting the is constant value to 10,800. Okay. Constant are valid for the entire time of a program runs within the scope they were declared in. Blah blah blah. Okay. Okay, cool. So we saw variables, mutable variables, constant, and then we take a look at shadowing. So you can declare variable in the same scope multiple times, or rather you can create a new variable with the same name as the previous one, and then you would shadow it. For example, if I redeclare x as 6, then I would print I cannot. This is a warning. Very cool. So the compiler understands that mute is not used anymore, like not relevant anymore, so you can remove it. Nice. Again, very impressive stuff. We can show the variable by using the same variable name and repeating the use of let word as follows. Okay, and basically here it shows that you can actually okay, this is okay. This shows that basically, I guess, so I would guess that the last print line would print 6 and not 12. Let's see. Exactly. Okay, makes sense. Okay, this is pretty straightforward, and this is basically we can change the type, blah blah. Okay, this is pretty like relatively easy. However, if we try to use mute for this version, okay, so this is pretty easy. So I would just my personal like, I understand why this works, and that maybe sometimes is useful. I would say let's just never do this. Like let's just never actually redeclare the same variable name. This is only like a source of confusions. So let's just call this x1 instead, or whatever. So next chapter, data types. Okay, so every value in your Rust is of a certain data type. Okay, because it's a statically typed language. So the compiler must know the type of all variables at compile time. Okay, the compiler usually can infer what type we want to use. Blah blah blah. In cases when many types are possible, such as when we convert a string to a number type using parse, we must add a type annotation like this. Okay, so love how it's like it's by default that you don't have it, and this is called annotation. Without like this is a bit weird. Also cool that you can not always specify it, so you can avoid things in Java like string my string equals new string. This is the fun. I mean, I guess this is the old Java. Now you can just use var. But anyway, cool that we can also not have the type. But okay, sometimes you need to help the compiler a bit and specify it explicitly. Otherwise, you will say consider giving us a type. Type annotation needed. I will consider giving us a type, but this is an error. Okay, I guess you kind of must. Scalar types. Scalar type represent a single value. Okay, like a number or something. Rust has 4 primary scalar types: integers, floating point numbers, booleans, and characters. Okay, integer, we have a bunch of different values of different data types. We have signed and unsigned integers, which this already says like that this is a system programming language when you have unsigned data types. Okay, so integer types start with I instead of U. Okay, and then it's pretty self-explanatory. Oh, this is cool. Arc. Are we explaining what arc is maybe later? Well, anyway, each variant can be either signed or unsigned as an explicit side. Okay, signed numbers are stored using 2's complement representation. Okay. Yeah, okay, so this is basically like normal most programming languages store these values. Additionally, the I size and the U size types depend on the architecture of the computer the program is running on. Cool. Which is denoted in the tables as arc. 64 bits if you're on a 64-bit architecture, and 32 otherwise. Okay, this also screams system programming, which is cool. Actually, maybe I am just ignorant and every major programming language also supports this. I actually never saw it. And I'm pretty sure Java does not, or Kotlin, they do not support this. Rust defaults are generally good places to start. Integer types default to 32-bit. Okay, the primary situation in which you'd use I size or U size is when indexing some sort of collection. What does it mean? Which kind of collection? Anyway. Oh, you can actually store them in a bunch of different literals expressions. Cool. But let's see about integer overflow. Let's say you have a variable of type unsigned 8-bit that could hold values between 0 and 255. If you try to change the variable to a value outside of that range, for example 256, integer overflow will occur, which can result in one of two behaviors. When you're compiling in debug mode, Rust includes check for integer overflow that cause your program to panic at runtime. Okay, when you're compiling in release mode, Rust does not include these checks, and instead an overflow occurs, and then okay, you get a 2's complement wrapping. Okay, so the values 256 becomes 0, 257 becomes 1, and so on. Okay, to explicitly handle the possibility of overflow, you can use this family of methods. Wrap in all modes with the wrapping methods, such as wrapping add. Okay, so basically, I understand. So you can cool. You can use this family of methods provided by the standard library for primitive number types. Return the non-value if there is overflow with checked methods. Return the value and a boolean indicating whether there was overflow. I wonder how this actually look. Like how do they even work? Like let's say you wrap an expression that could overflow with a wrapping add. What does it actually mean? Is this a macro that adds some stuff? Oh shit. Well, what is happening? Yeah, I think we arrived at data types. Specifically at this wrapping add. So I wanted to check an example of how this looks. And return up plus. Oh, okay, I understand. Okay, this makes a lot more sense. Okay, so basically you don't write the sum yourself. The sum is implemented inside the method. Okay, makes sense. So that's why they are not a macro. Okay, makes sense. Floating point types. Okay, Rust also has two primitives for floating point numbers. We have 32 and 64-bit variants. Okay, this look basically as every other programming language. Numeric operation, they also look the same. Booleans also look the same. The main way to use Boolean values through conditionals, such as if expressions. Okay, we know this. The character type. Rust char type is the language's most primitive alphabetic type. Here's some example of declaring char values. Okay, cool. So one emoji is one character, which means something UTF-8 or whatever. Rust char type is 4 bytes in size and represent a Unicode scalar value, which means it can represent a lot more than just ASCII. Accented letters, Chinese, Japanese, Korean characters, emoji, 0 with spaces are all valid, blah blah. A character isn't really a concept in Unicode, so your human intuition for what a character is may not match up what a char is in Rust. Yeah, because I think, wasn't there something like for, okay, I don't want to, I am too tired to say for sure, but I think a char in Java is only 8-bit, 16-bit. That makes sense. Okay. Outbit. Okay, so two bytes. Okay. So for example, an emoji in Java would be 2 characters, not 1. But okay, compound types. Compound types can group multiple values into one type. Tuples and arrays. Okay. The tuple type A tuple is a general way of grouping together a number of values with a variety of types. Okay. Cool. So this is very cool. So basically tuples are collections, but you can have different types with them. Like it wouldn't be trivial to implement something like this in Java with type safety. For an arbitrary set of types. So very cool to see this. Binds the entire tuple because a tuple is considered a single compound element. To get individual values of a tuple, we can use pattern matching to the structure tuple value. Oh, wow. So this is also cool. This is also something you can do in Kotlin with data classes. I wonder how I can... Oh, okay, they are indexed like this. Okay. Okay, this is a weird syntax. But we'd like to make the blah blah. We can also access tuple element directly by using a period. By the index of the... Actually, if you think about it, this makes a lot more sense than what I would have thought this would be, which would be like a array access, like something like this. But actually, why do array need to use a special syntax? Like, this is what you would have expected if you learned how to access array values after you learn how to access member properties of classes or whatever. But still, it looks very weird. This program creates the tuple x and then accesses each element of the tuple using their respective indexes. Okay, we know this. I mean, we know. Okay, we can assume. The tuple without any values has a special name unit. Okay, I wonder what happens if I create a tuple which is, for example, string, was it capital? String, and then u8, which is hello and 2. So this compiles, right? It does not. Okay, so I don't know Rust enough to understand this properly. Let's just say that this is a reference to a string, whatever this means. Yes, I understand that this is unused. And then let's say I do 3. Nice. Oh, okay, I see. Oh, okay, so basically this is at compile time generate. Okay, makes a lot of sense. Okay, so the compiler can know that you cannot do this. Okay, makes sense. Cool. The array type. Multiple values is an array. Every element of an array must be of the same type. Okay. And they have a fixed length. Okay, makes sense. For example, we have months. Arrays are useful when you want to add your data located on the stack rather than the heap. I guess because you can do that because you already know the size. Or when you want to ensure you always have a fixed number of elements. An array isn't as flexible as the vector type, of course, because a vector can grow or shrink. Blah blah blah. What the will you write an array type using square brackets with the type of each element, a semicolon, and then the number of elements in the array, like so. Okay, so I mean, I guess this is fine because these are basically there are only two like fundamental collection of things, but it does look a bit weird. Again, this type. You can also initialize an array to contain the same value for each element by specifying the initial value, followed by a semicolon. Okay. Okay, also weird, but I will take it. And then we access array elements as you would expect. And I guess you also... Okay, let's see what happens if you try to access an element of an array that is past the end of the array. Okay, so let's see. Let's take a look at this code. So we have an array of 5 elements, and then we ask for an index. Okay, cool, because we cannot know it at runtime, at compile time. Okay, so we do the same as we did in the last example. Let me just copy everything. So basically let's also lower this thing. So basically we read the index from the user, then we parse it as an integer, as an unsigned size in number, and then we access an element, we access the array at that index. Let's take a look. Use of undeclared creator model IO. Okay, yeah, we need to import some stuff. Nine. And we panic. Okay, index out of bounds. Okay, but we can do this. I thought maybe the compiler would say no, you cannot access with an arbitrary index or whatever. But yeah, okay, this makes a lot of sense. Okay, so it's pretty late, and I think I am a bit too tired to look at functions. So yeah, I would say this was a bit of an underwhelming episode, but next episode will be about functions, and everybody loves functions, right? So maybe we can have something a bit cooler, a bit more code to write. This was basically just we have functions and then control flow, and then finally we go to the actual cool stuff about Rust, which is ownership. So I want probably functions and control flow is still too short to be one entire episode. So it could be I am already seeing go-tos here or whatever this is. But anyway, so I think this is probably too few content for one entire episode. So probably next time we are gonna start looking at ownership and borrowing and all these nice things that I constantly hear about on Twitter or on Mastodon these days. And we can check out what the hell they are. So yeah, cool. See you next time. Bye.